No need.
Okay, so for the direct comparison test, we throw away the insignificant terms and out pops a series. We use a comparison test on something that's not quite P series, not quite something that we can integrate, or not quite a geometric series. So we throw away the insignificant terms, and we do have something that is either P, geometric, or integrable. We test it, decide whether it converges or diverges, and then we compare the sizes of the terms of the positive term series with the one that looks like it. If it's smaller than a convergent series, then the series converges. If it's bigger than a divergent series, then the series diverges. So smaller than convergent is convergent. The other conclusion can be drawn if it's bigger than a divergent, then it's divergent. The problem arises if your series is smaller than divergent or bigger than convergent. Then this test doesn't apply. Then we go on to the limit comparison test. Or we can go to it before we even do this one if you want. So again, the same way, for our positive term series, we throw away the insignificant terms and we just form the limit. Suppose the limit as k goes to infinity of the positive term series that we're testing divided by the lookalike series gives us a number L. If L is a positive finite number, then both series do the same thing. If the limit is 0, and the series that looks alike converges, then a given series converges. If the limit is infinite and our given series diverges, then the series we're testing also diverges. This was the direct comparison test. And this one is limit comparison test.
And for both of these, we would use the same, like if you had,
Make the B gate about the same way.
okay.
Right, throw away the insignificant terms. And so the examples I worked last time. Oh, fudge. Oh, well. These are my examples. Let's look at, for example, we use comparison tests to determine if the given series converges or diverges. My first one is the series from k is equal to 1 to infinity of the natural log of k divided by 2k squared plus 3k. It would be a Q log series if I didn't have two terms in the bottom added to each other. I just had a single term, right? So of the two terms that are in the bottom, this one has the highest power. So I'm going to build my lookalike series just by throwing the 3k away. So let's let my lookalike series look the same way with the logarithm on top, but let's keep the 2k squared on the bottom. So that now is a Q log series. Q is equal to 2. Does that tell me whether or not it converges? It does. It's bigger than 1. So this converges. So my lookalike series converges. Is the given series smaller than this one?
Yes.
It is. It has a larger denominator. 2k squared plus 3k is bigger than 2k squared. So when I flip the sides of this inequality, this one is smaller. And now if I multiply both sides of that inequality by the natural log of k, I have that my given series is smaller than a convergent series. And so now I state my conclusion. Our series is smaller than convergent. So it converges. And this was the direct comparison test. Smaller than convergent is convergent.
You want us to include what test we did in our answer?
Yep, don't make me guess. All right, so this one's just about as quick. Move the camera a bit. So the sum of 1 over the square root of k squared plus 1. It would be. We're going to compare it to a p series, right? If I didn't have that one here, then what's left is a p series. So that's my comparison series. Pick your bk to be the square root of k squared, which is just our series 1 over k. The p series where p is equal to 1. That one's called the harmonic series. It's used a lot to describe things that bounce back and forth. But what do we know about the p series where p is equal to 1? It diverges. So my bk's diverge. Is the given series bigger than the divergent series?
No.
No, it's smaller because it's got more in the denominator. Smaller than divergent doesn't tell us anything. So we've got to use the limit comparison test. This is not bigger than that. It's smaller than that. It's got more in it. Okay, so we need to use the limit comparison test since the sizes go the wrong way. where we take the limit of the given series divided by the one we built. The given one looks like 1 over the square root of k squared plus 1, and ours is 1 over k. So that's the AK divided by the BK term. So we'll do the flip and multiply step to help us take this limit a little bit better. That'll put the k up here and the square root of k squared plus 1 here. Can you tell what that limit is going to be? That limit is 1. So we get a positive finite limit. The limit comparison test, if you get a positive finite limit, both series do the same thing. Right, they behave in essentially the same way. So both series do the same. I look up here, my comparison series diverged, so my given series diverged.
Yeah, it's a series.
Last time we did this example, we broke that up as partial fractions and saw that that thing is a telescoping series. We don't have to do that now. We can determine that it converges or diverges. It's going to converge if it's telescoping, right? We can think of our denominator as a second degree polynomial with lower degree terms, right? So instead of breaking it up as a telescoping series, we can compare to multiply that out, I'd get a k squared plus lower degree terms. Right? All right, does that particular series that I compare it to converge or diverge, and why?
It converges because P is greater
It's a
than,
P series, bigger than 1, so this one converges. Is the given series smaller than a convergent series? Yes.
Yes.
Yep, the given series has more in the denominator with the same numerator. So it is smaller. 1 over our k squared plus what would be in the middle, 5k plus 6 is smaller than 1 over k squared. And so our conclusion is smaller than convergent is convergent. By our direct comparison test. So it's an easy test to do when the sizes are obvious. We could also have done the limit comparison test. Had we done the limit comparison test of the stated series with 1 over k squared, what would the limit have been?
0.
1.
Oh, yeah.
Limit would have been 1 because now it had a k squared on the bottom, a k squared on top. The ratio of the coefficients gives us 1. So we have a positive finite limit, both do the same. Okay, so the limit comparison test is just as easy. Right, next term. Let's put some terms in both the denominator and the numerator. Let's put the series here. Test has a square root of k on top. The cube root of a sum. Let's see, let's go with k cubed plus 1. And then let's multiply that by, how about the 6th root of k? That's the 6th root of k. Let's make it the 6th root of k to the 5th. Square root of k divided by the cube root of the quantity k cubed plus 1 times the 6th root of k to the 5th.
And I assume the sum goes to infinity.
Sum goes to infinity. So that's the clue that you've got a comparison test. You got a bunch of k to the powers added, subtracted, multiplied, bunch of k to the powers. Yes, sir.
You keep going, because I think I'm getting ahead.
So the only thing that isn't a k to a power is that silly 1. So that's how I make my comparison series. Throw that 1 away. And try to write that as a p series. Okay, so I'm just going to throw this 1 away and combine all my powers and see if I got a p series going on here.
For k over 11, 6. Or k to the over 6.
Right, if that wasn't one there, then it'd be a p series already, just a little work to do. So we throw the 1 away and that's our bk series. So we pick the bk. Look like, let me write them as k's to a power. So that'd be a k to the 1/2. When I throw that 1 away, that's just a k cubed, then a cube root of that. I'm just gonna write k. And then a 6th root of k to the 5th. What does that look like? K to the 5/6.
Now we have 11 over 6 minus 1/2.
All right, add exponents. So I have k to the 1/2 divided by k to the 11/6. Now subtract exponents. So that's 3/6 on the top, 11/6 on the bottom, 11/6 minus 3/6, 8/6 or 4/3. My gosh, we finally have a p series. P is 4/3, which is larger than 1, so it's a convergent p series. The only thing I did to get from the given series to my series is I took a 1 out of the denominator. Technically a cube root of 1 kind of term. Does that change? Can you compare the size between the two? This has a bigger denominator. So the overall fraction is smaller. Right? So I can use the direct comparison test. AK is smaller than BK. It has more in the denominator, kept the numerator the same. BK converges, so my conclusion is smaller than convergent is convergent.
Is that a common phrase, or is that just like a?
That's just what I say, so I can remember it. It's gonna be you're gonna have a whole bunch of tests, and you're gonna have some way to remember all of your conclusions. So if I just keep writing it when it happens, maybe you'll remember it. If you don't, I keep doing one of these.
I think it makes sense.
Smaller than convergent is convergent. Okay. All right, and I'm gonna put a bunch of terms both in the numerator and the denominator. So on number 5. Gosh, that's got a lot of Ks in it. Any feelings about whether this should converge or diverge? Because?
It looks like a P series and you have 1/K and then.
Right. Look only at the highest powers of K, the numerator and the denominator. Highest power of K in the numerator is a K squared. Highest power in the denominator is a K cubed. So if I build my BK series, I keep the K squared, the K cubed, and throw all the other stuff away.
Oh, yeah.
We'll go ahead and keep the 3/4. The 3K squared over 4K cubed, which simplifies to a 3/4K. Well, the 3/4 doesn't matter. What's left is kind of a 1/K deal. What do you know about the 1/K?
Divergent.
Divergent, that's a divergent P series, P is 1. Can't really tell if the given series is bigger than the one I have because I threw terms away from the numerator and I threw terms away from the denominator. So instead of worrying about how the sizes compare, I'll just do a limit comparison test. Take the limit. As K goes to infinity, you take all of the AK and divide by the BK. So I'm going to take that and divide by 3/4 to the K. Take longer to write than to do. So I'm going to ask if you let me skip a step. When I'm dividing by 3/4K, my next step would be to take the 3/4K and flip and multiply. Can I go ahead and skip to that step? 4K up here and the 3 there. So when you distribute that 4K through the numerator, you're going to have a 12K cubed plus lower degree terms. When you distribute the 3 through the denominator, you're going to have a 12K cubed plus lower degree terms. What's the limit going to be?
1.
And it's going to be 1, right? A 12K cubed plus blah, 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 and a 12K cubed plus blah, blah, blah. So that limit is going to be 12/12, which is 1. It doesn't matter the size of the limit, as long as I get a positive finite number. We shouldn't get negative numbers because we're testing positive term series. Positive finite limit says that they both do the same thing. Again, I'm just writing this to help you remember the conclusion of the test. Go back and look at what the BKs did. It was a divergent series that we compared it to. So our given series compare. So they both are divergent.
Do an example of where we're looking at bigger than divergent is divergent.
Bigger than divergent is divergent, okay. Let's see, I think I went off the top of my head. There, let me do that in the next example. Just divergent. Okay, this should work. This should work. Okay, I got a k squared of minus 4k on top. If I want this to be a positive term series, let me start my k at 2, so I don't have any negative terms. Who wants to tell me what I'm going to compare it to? Compare it to 1 over k? Keep the k squared from the top, the k cubed on the bottom. So that I can compare it to a divergent p series. Now, the given series has less in the numerator, but more in the denominator. Nope, I should have made it the other way. But smaller. I got it smaller than divergent. Okay, I can't do it. That's not the way I wanted it to be.
We're going to do a limit.
We'll have to do a limit comparison test, right? Because this has less up here than this does, but it has more down here than this does. So less over more makes it less, right? So it's smaller than divergent. It's not in the right size. So I'm going to do the limit comparison test. So we take the limit as k goes to infinity of the given series over the one we just built. Given series has all this stuff on it. K cubed plus 3k squared plus 5. Then I'm dividing by 1 over k, so I'll do the flip and multiply.
You get 1 again.
And our limit's going to be what?
1.
Limit will be 1. So we get a positive finite limit. Both do the same. And so both are going to diverge. All right, let me think harder. Where can I go bigger than divergent?
I would maybe,
Just do like 1 over 3 minus 1.
Yeah.
Oh, okay, okay. Yeah,
Makes sense.
duh, don't work so hard.
Even though we state that it's a positive finite limit that says that they both do the same thing, do you still want us to label it as a limit comparison test?
Yeah, I always label the test before I try it.
Okay.
So that I know it, so that you know what I'm attempting to do. Because we're gonna have other tests that look at ratios. And so I don't want you to get confused. All right, so let's see, number 7. The cosine squared of k times the square root of k all over k to the 4th. Let's just leave it like that. That look like something that lends itself well to a comparison test? Why not?
Doesn't look like anything.
square root of k is always no greater than 1.
That's right. Cosine squared is always positive and no larger than 1. right? Cosine lives between 1 and -1, so cosine squared lives between 0 and 1. So this is no larger than 1. So in my comparison series, I'll just put a 1 right there. And keep this and this. That's my BK series. That simplifies to a P series again. What's the power going to be when I simplify that? How much? 7/2. 4 minus 1/2 is 8/2 minus 1/2 is 7/2. So P is 7/2. What do we know about P series where P is 7/2? Converges. Okay. You want to use a direct or limit comparison? Does it matter to you?
Direct.
I'd rather do the direct comparison test because the limit of cosine squared of k doesn't even exist. Limit comparison test isn't going to do us any good because that limit goes between 1 and -1. Right? So limit comparison test is not good in this case because this thing doesn't even have a limit. So we're going to do a direct comparison test. This numerator here is smaller than this numerator because I put the largest value of this function in there. So now if I divide both sides by the same positive number, the inequality stays the same size. And so I've got smaller than convergent is convergent.
Isn't it sometimes equal though?
Yeah, but for the most part,
That's fine.
yeah, that's fine.
I'm not that nitpicky.
Just about always smaller than convergent is convergent. Here's when they're equal.
It's 6k to the 4th.
Whoops, that is
Okay,
a to
okay.
the 4.
That's what I was missing. Okay.
I just needed some more black stuff on my fingers, so I wrote it something I can erase with.
Makes sense.
Makes sense that I like to erase with my fingers. Let's see, do I have any more comparison test examples? Oh, they all look like that. It's a really easy test to use. And we use it just like you gotta make sure you know when you use things. You use it when things look like a bunch of stuff added together. Looks almost like what we know stuff. Let me find one more because I didn't use.
So if we had a sine squared of k, it could be the exact same thing.
Yep.
But not necessarily, or definitely not.
What would you do for this one? What was that? That was number 7.
I guess you could do tangent squared.
Square it.
K times the arctangent of k divided by k plus 1 times 2 to the k. This is something that you can compare relatively easily.
Well, you know that the arctangent of k is constant. When it goes to-
Arctangent of k has a limit.
Well, yeah, basically it goes to constant.
At its very largest, what is the arctangent of k going to be?
5/2.
Pi over 2. Very largest, it's pi over 2. So if I keep the K there, and put a pi over 2 here, I've made the numerator bigger. And then if I just throw the 1 away, I've made the denominator smaller. My numerator is bigger. And my denominator is smaller than the original one,
Which makes it bigger.
which makes this one bigger than that one, right? So we got the size going here first. Can you tell me what kind of series this is? Well, we can get rid of that. Pi over 2 is a constant. It's a geometric series. Right, pi over 2 times 1 over 2 to the k. So what kind of geometric series? Do you got a convergent or a divergent geometric series?
Conversion,
Because,
it's less than one,
what's the r?
1/2.
R is 1/2, smaller than 1, so it's convergent. So our BK series is larger than the AK series and is convergent. Do we have a conclusion?
We do a limit test.
No.
Wait.
Smaller.
Our series
Never mind. Okay.
is smaller than convergent. So putting these two things together, we're done. Smaller than convergent is convergent. Okay? P-series, geometric series, stuff that we know how to integrate, stuff like that, then we can do a comparison test. Okay? Yeah, they all look alike. I don't have anything else to say about that. So I guess that means, unless you have any questions, we'll go on to the next section. What made these jump out as comparison series is summing. Sums and differences in the numerator, sums and differences of k's to powers. So when we have products, or another version of a product would be a factorial, then I'm going to show you some other tests that are good for those.
We use
Factorials.
What's a factorial?
Exclamation point.
What does this mean? N,
Yes, sir.
what is that?
N times n minus 1 times n minus 2, and then each one.
All the way down, right? So what is the value of 5 factorial?
Times 4 times 3 times 20.
Yeah.
How much? 120. So n factorial means n minus 1, n minus 2, and get it all the way down to 1. They're
So really what we're
products.
doing is we're like infinite foiling.
Infinite foiling. But it's a monomial instead of a binomial.
Wait,
Can I what?
can you take like n minus 1 in parentheses, can you take that to the factorial?
You can? We're gonna-
1 times n minus 2 times n minus 3. You're just
Whatever
shifting-
integer n minus 1 represents, remember n's a integer, positive integer. So you start with that integer, go to the one before it, keep multiplying until you get down to 1.
What about n minus 1 squared?
And then you have a
Like in
pair of them.
parentheses, yeah.
Then you just put another one here and put another one there. What about this? What does that mean? Say again?
I think it's 2n minus 1 minus 2n minus 2.
Yeah, 2n first.
Is it not?
2n first, then 2n
2n
minus 1.
first.
Doing this first.
And then 2n minus
N
1.
minus 1. 2n minus 2.
Until we get to 1. What does this mean?
2 times.
2 times, that's that with just a 2 in front of it, right? So the parentheses are
Parentheses change
important.
things,
Parentheses are important.
What's the end of the factorial?
Ah, big.
It's a
Why?
really, really exciting.
Okay. So we're gonna look at series that have factorials in their terms and series that have products entirely numerator and denominator. So series that have lots of products or factorials or n powers. So in section 8.5. 5, I said.
Is there any way to
Hi.
make this not an integer, like factorial like 4.5 and stuff like that?
Not with that notation.
Okay.
Counting number is a whole number. So I'm going to say 8.5. So now we will consider series whose terms involve products, factorials, which is a product, and n powers. Like a power of n. These are things that we need a test that has canceling in it. So we're going to need to do some sort of dividing where we can cancel common factors. And the test that we're going to have something called a ratio test. It handles just about every single case of these. And then a special case of the ratio test will be the nth root test. So if we've got a series A, if I'm talking about n's here, so I'm going to call my series AN. That's the series that we're testing. We're not going to build a lookalike series. We're just going to compare adjacent terms in a limit. So if I go out here to the nth term and then go to the term right next to it, to the n plus first term, I'm going to look at the ratio of the term on the right with the term on the left. And the size of the limit is going to tell me whether or not that series is going to converge. So we will consider the limit as n goes to infinity of the term on the right, that would be the n plus first term, divided by the one right before it. So we take this limit, it's either bottom heavy with limit 0, it could be top heavy where the limit's infinite, or it could be some limit where we look at the ratio of the coefficients. So let's just say it's got some limit L. First case, if L is smaller than 1, then what can we determine about the way the terms follow each other? Because
Each term is a bit smaller than. the term
it's
before
smaller
it.
and smaller and smaller, right? So if that limit's smaller than 1, then the previous term is bigger than the next term. It's getting smaller and smaller and smaller as a product. And so the series converges. Then the series converges. Right? What happens if the limit's bigger than 1? Because if it's bigger than 1, the next term is going to have to be bigger in size than this one, even if it's slightly bigger than 1. Which means as I'm marching down here, right, this looks like A1 plus A2 plus, and here I'm going out to the nth term. And then I got one right next to it. If this limit's bigger than 1, then that guy's bigger than that one. And that's not good. And the series diverges. And the problem with this test is if the limit's equal to 1, we make no conclusion whatsoever. They're kind of marching in unison, but we don't know which way. Are they going to converge eventually, or are they both going to diverge? So if L is equal to 1, we got to try a different test. This test is inconclusive. When students attempt to use a ratio test, just because it's so fun and cool to use, on things that you should use a comparison test to, you're gonna get a limit of 1. Because if you got a bunch of stuff added together, you don't get nice cancellation. It's when you have things that are multiplied, and factorial, and n powers that things cancel. That's the ratio test, so we're looking at things that are bunch of products. So consider the series that has 2 raised to the k power on top and k factorial on the bottom. So let me ask you, I started my counter at 0. And I put a k factorial on the bottom and I didn't screw up.
That's 1.
0 factorial is defined to be 1. So is 1 factorial. 1 factorial is 1. By definition, 0 factorial is 1.
Can you explain that?
I don't know,
I won't.
just to make everything complete. It's just by definition.
What's that? Can you do negative factorials?
There's no such thing as a negative factorial because we have to go down by 1.
But you could just go down by 1 to infinity?
It sounds like fun.
Just start going up by
Use
1.
I
infinity, actually.
These are positive term series, so our counters are always counting positive. Right? When you program in computer science, you don't make your counter go back negative, do you?
I mean, you can.
Yeah,
You
Jackson.
can, but you don't, because then you would just adjust your counter so it goes forward. So just for
Depends on how much
completeness, we
you're
define 0 factorial as 1. So I can write something like this. But there aren't any terms to throw away. I couldn't compare it with anything, right? And remember in our tower of power, what grows faster? Does 2 to the k grow faster than k factorial? Well, it does. Compare 2 to the 1, 2 squared, 2 cubed with 2 factorial, 3 factorial. Compare 2 to the 10th with 10 factorial. 2 to the 10th is 1024. 10 factorial is big. 10 factorial is much bigger than 1024, right? So I'm saying that so that you know that this has a limit that goes to 0.
Yep.
That we should go ahead and do a test. Numbers to a power in our tower of power are up high, 2 to the power, then maybe 3 to a power, bigger the base to a power grows faster and faster, but then n to the n grows faster. But somewhere in there, n factorial.
What was the topic?
I don't know what's on the top. N to the n. If you wanted n factorial, the n factorial, I bet that's faster. You can continue. The tower of power has no upper bound. Okay, but anyway, I couldn't do a comparison test because there's nothing to throw away. There aren't insignificant terms added or subtracted. So I'm just going to take the ratio of the current term and then build the next term by replacing each of the counters with counter plus 1. So I'm going to look at the limit. I've chosen k's as my counter. So this time I'm going to look at the limit. Let me try a new marker here.
Do we still have to check for if it's continuous and such?
We're not integrating it,
Okay.
but I did a quick limit to 0 test, right?
Okay.
All right, so I'm going to look at the limit as k goes to infinity. I take my k plus first term, so replace each k with k plus 1 and divide it by the series as you see it. So I've got 2 to the k plus 1 divided by k plus 1 factorial. That's my k plus first term. Take each k, replace by k plus 1, and then put the operation on it. Then divide by the series as you see it. 2 to the k divided by k factorial. So I'm usually going to skip this step and go straight to the step where we flip and multiply. All right, so we'll always get a step where we have to flip and multiply. I'll skip to that next time. My 2 to the k plus 1, k plus 1 factorial. This k factorial will be on the top. And this 2 to the k will be on the bottom. So
You could subtract the k out, so it just becomes 2 over k.
let me go back to here. There's n factorial. Here is n plus 1 factorial. It starts at n plus 1. And then the one before that
Becomes n.
would be n. Then the n minus 1, n minus 2 until I get down to 1.
You could divide out everything and just get the.
So do you agree that n plus 1 factorial can be written as n plus 1 times n factorial?
Yes.
And n plus 2 factorial would be n plus 2 times n plus 1 times n factorial? So that's how I'm going to write the k plus 1 factorial. I'm going to write k plus 1 factorial is k plus 1 times k factorial. I can break up the 2 raised to the k plus 1 power. Because I know that when I multiply like bases, I add the exponents. So 2 to the k plus 1 is equivalent to multiplying 2 to the k with 2 to the 1. Let me write that step in. That's 2 to the k times 2 to the 1. And I've got a k factorial up there. Downstairs, I said I was going to write the k plus 1 factorial as k plus 1 times k factorial. And then I've got the 2 to the k. So you can see what cancels? K factorials cancel. 2 to the k cancels. And I'm taking the limit as k goes to infinity. 2 divided by k plus 1. What do you think?
0.
0. Limit is 0. Limit is smaller than 1, converges. And all of this is the ratio test. Students love to do the ratio test.
It's kind of cool.
It's cool. It's
That's
easy.
right, RT. You know what that means?
RT, ratio test. But then we have a root test.
What about NRT?
RT. Unless I use a K, then it's a KRT.
That works too.
All right, so let's get something bigger. Bigger, bigger, bigger. Okay, so this is gonna start bleeding together, because what makes a P series converge?
That's greater than 1.
Oh, so what makes a limit comparison test converge? Oh, it's smaller than 1. Makes a Q log converge?
One.
Q is bigger than 1. What makes the limit comparison test?
About one.
Any
Something with
limit,
zero, I
right?
don't know.
Any limit comparison test. So there's all different sizes you gotta remember. So what I suggest is that you start making your little note cards to help you remember these. Okay? They're gonna start bleeding together after a bit.
I think if you just think about it for a second, it kind of makes sense.
If you
but-
do think about it for a second, but thinking and math, it's always hard to get you guys to do both things.
You
It's
kind
like
of have to
chewing
choose one
gum
or the
and
other.
walking.
Yeah, I can't do that.
Messing
Can
up
you chew
my-
gum, walk, and think math?
No.
That's
I
literally
can't think and
logically
do
impossible.
math.
You can't think and do math?
So why bother adding on the walking and chewing gum to it?
Because I'm hoping one day that when you can do all three, you are ready for a life in academia. Plus, you have to like walk down the road by yourself and talk with your hands. You ever see that? You tell somebody they're just, that's my husband. He's just,
That's a professor.
who's this invisible person you're talking to? Are you cussing me out again?
You know, I saw somebody doing that, but he had a really big beard.
Yeah, there's
Wore a
another
beanie.
sign. There's another sign that you're in academia. The beard gets really big.
He may have been pushing.
And then
a
there are the
shopping
male
cart
faculty
also.
members.
Pushing a shopping cart, that
He
poverty is
also,
associated with academia.
It just get weird when all you do is think about math all day long. Or any academic subject.
say math or math?
I mean, both are true.
Any academic subject does that to you.
I'm-
Okay, so how about,
Pursuing this all the way through.
you wanted squares? Let's do this.
I don't hang out with squares.
Here's our second one. Test this one.
No, I don't. It seems like that's so.
Yeah,
You're
rotund.
You're a little bit rounder than a square.
That's a rectangle.
I'll go with that.
About that. What happened? It's not on it? This way I gotta go. I gotta go, maybe that way. Bum, 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 bum. There it is.
Oh, wow, okay.
Okay, so you see factorials. That should also make you excited. That's ratio test. Factorials,
That's why
ratio
they have the
test.
explanation.
Okay, so that's your giveaway. Powers, factorial, ratio test. So you're gonna tell yourself what you're gonna do. You're going to consider the limit as the counter k goes to infinity. You're gonna increase k by 1, build the ak plus first term, and divide by ak. Let me see if you can do that part. Think of k plus a k factorial squared as just a pair of k factorials multiplied together.
Okay.
Be careful when you make the k plus first factorial for the 2k factorial. So you're taking the k out where it is, and you're gonna put in a k plus 1. And then you're gonna do the remaining operations on the k plus 1.
So should it be 2k plus 2?
So it'll be 2 times the quantity k plus 1, then the factorial. So you're right, inside will be a 2k plus 2 factorial. Right, so I'm just gonna put that step in. Where the k is, you put a k plus 1, then you multiply by 2, then you put the factorial. Same deal here, but I'm gonna write that like this. I'm gonna write that as a pair of k plus 1 factorials. Here's the ak plus first term. Then we're gonna skip to the divide by the other fraction by flipping it over and multiplying. So I'm gonna take this, flip it over and put it here. I'll give you a minute to simplify this. See what cancels. Tell me where you are when you get the limit. What number did you get? 4 should be your limit. Need help getting the 4, let me know. With all the canceling,
Quickly canceling.
you should get 4 for your limit.
How do you factor 2K to factorial again?
That's itself, and then itself minus 1, itself minus 2. But that doesn't matter because this is going to be 2K plus 2 factorial, which would be 2K plus 2 times 2K plus 1 times 2K factorial.
Okay, then it goes on from there.
Got a new marker in here. Which one was my new marker? Anybody else getting a limit of 4? That's not my new marker. Okay, so I said I was going to replace that. Yeah. Take it up to here. Ew. It's smushed. 2K plus 2 factorial is 2K plus 2, and go down by 1. Then go down by 1, and it puts us at 2K. So all the rest of it match the 2K factorial. Then K plus 1 factorial does the same thing, starts at K plus 1 and then multiplies with K factorial. And so does the next one. K plus 1 by itself, then K factorial. Then I got that other guy up here. Got a K factorial here, K factorial here, and a 2K, all factorial. You with me to that? And so my K factorial here cancels, and here with that one and that one. 2K factorial cancels with all of those. So that's what's left.
Just a two there.
So I got a second degree polynomial on top and a second degree polynomial on the bottom. When the degrees are the same, the limit will be the ratio of the coefficients. So here I've got, when I multiply this out, a 4K squared plus lower power terms. And on the bottom, I have a K squared plus lower power terms. So our limit's going to be 4, and then we make a conclusion. If the limit's bigger than 1, series diverges. Okay. There's some where this limit can become interesting. I'm going to look at say this series, that series, and this one. Limits are difficult. So it's best if you knew of these two, which one diverges right off the bat.
Yeah, right.
Because
Power.
higher power on top goes faster on the top. This diverges by the test for divergence. This one, we're going to do the ratio test, but we're going to encounter a very difficult limit. like how one students can do it, because we just covered it today.
Well, isn't it just power anyway?
Limit to zero tells you nothing.
Oh, yeah, okay.
Limit not to zero tells you it diverges.
So is that one converges?
I don't know. We'll have to find out.
Okay.
We'll find out next time.
And then today.
Everybody wants to leave.
That's what I was thinking, something like that.